Welcome back, everyone. So in this video, we're going to be discussing the Doppler effect. Now, the Doppler effect is a phenomenon that occurs with all sorts of types of waves, sound and light. For our purpose here as human beings on Earth, we're going to mostly observe it with sound. It does happen with light, and I'll talk about that briefly later in the video here, but for our purposes, for the main chunk of this video, we'll be referring to sound with the Doppler effect. Okay. Now to start, let's just quickly define the Doppler effect and kind of talk about what that means. So the Doppler effect can be defined as the following. It is the apparent change in frequency due to the relative motion between the source of a wave and its observer. So let's break that down just a little bit, just briefly, before we get into pictures and diagrams and scenarios and stuff. So let's start with the apparent change in frequency. What that means is the frequency doesn't actually change. Okay, if I were to let out a certain frequency, let's go with ah, okay, that frequency, me being the source, will not change. Okay, the observer might hear it differently, but that frequency ah is not changing. Okay, now let's break it down to the second part. Due to the relative motion between the source of the wave and the observer. So let's quickly talk about what relative motion means. Well, basically it just means, are the two objects moving further away from each other, or are they moving closer to each other? Okay, so if I'm sitting here and there's somebody else standing right behind me, we're both at rest, there is no relative motion, right? One person is not moving relative to another person. We're both just sitting there. In other words, the distance between us is not changing. Now, let's say we were both to start walking. If we're both walking at the same speed, we're standing side by side and talking, there's also no relative motion. We're right next to each other. The distance between us is not changing. Right? So that relative motion talks about, are the objects moving further away, or are they getting closer together? Right? And how those two objects are moving in relation to each other, relative to each other, will determine how that frequency is perceived to change. So let's kind of go through a scenario here. Let's say you've got a police car, okay, and I'm going to draw my very classic police car. Okay, I mean, if that's not a police car, I don't know what is. All right, now this police car is going to have its siren going, pew, 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 okay, which means that each one of these lines represents that pew. Okay, now, if the police car is stationary and you've got someone over here, okay, also stationary, the distance between these waves will remain the same. Okay, so this car is just letting out the pew, pew, and this person's hearing pew, pew, because as the waves travel through the air, they reach that person, that observer, at the same frequency. Okay? Now, let's imagine a scenario where the police car is catching a bad guy. Right? Some kind of criminal is out there. Maybe, I don't know, someone copied a TikTok or something. I don't know. I'm not a doctor or anything. And now, here's our observer over here. Okay. But now the car is moving toward the observer. Right? Well, what's going to happen is that a siren will go off, pew, and as the sound wave is moving toward the person, so is the police car. So when they let out another pew, it actually sort of almost kind of catches up. Okay? So now we have pew, pew, right? So the frequency has actually increased, right? We see a decrease in the wavelength, and for the same speed, v equals f lambda, frequency times wavelength, that frequency increases. So this person hears a higher frequency. So while the police car is still letting out pew, pew, this person will hear something closer to pew, pew, because of the fact that they're moving closer and these waves are sort of getting squished. Okay, so as the objects move closer, the apparent frequency heard by the observer increases. Okay? Now, let's take the flip side of that. Okay? So we'll have the police car having left that general area and is moving now away from the observer. Okay? The police car is still letting out their pew, pew, right? So it's pew, let out a wave. But now, as the wave is moving toward the observer, our police car is still moving that way, the car is moving away from the sound wave. So it's almost like the next one is sent further away. Right? So now the waves are a bit further apart. That wavelength is further apart. A higher wavelength will lead to a lower frequency. So while the police car is moving away from the observer will hear something instead of pew, pew, which is what the police car is letting out. The observer will hear something more like pew, pew. Okay? Now, I'm exaggerating exactly how much those frequencies will change. It depends on how fast the car is moving and so on and so forth, but those are just the general effects, right? As they move toward, the frequency increases. Here, as you can see, as the object moves, or the source in this case, moves away, the frequency decreases. Okay? The same effect would be heard if the source was stationary and the observer was moving toward or away. So if it was moving toward, the observer would hear an increase. Moving away, the observer would hear a decrease. Or if they were both moving, right? If they're moving in opposite directions, or maybe if they're moving in the same direction, but one's moving faster, all sorts of different scenarios. Bottom line is, if they're moving farther and farther apart, you're going to hear a lower frequency. If they're getting closer and closer together, you're going to hear a higher frequency. And that's it. That's the Doppler effect for sound. Now, I did promise that we would talk briefly about the Doppler effect as it pertains to light. Now, light moves far too fast for anything here on Earth to really be observed by any person or anything like that. But if the object is big enough and moving fast enough, we can observe this elsewhere. So, for example, we were able to prove, for lack of a better term, that the universe is expanding because the scientists that won the Nobel Prize for this observed that the spectrum of light that they were getting from faraway galaxies was a little bit redder than what they expected. A red light has a lower frequency than blue light. So if it was shifted to the red end of the spectrum, red shifting, we know that it was moving further away due to the Doppler effect. Right? And that is why we say the universe is expanding. Many of these astronomical features, galaxies, nebulas, so on and so forth, are moving away from us. We see their spectrums being shifted toward the red end of the spectrum. Okay? Now, there is even one object that we know of, at least, the one I'm going to use for this example, that is blue shifting towards us, right? So moving closer, and that's the Andromeda galaxy, right? At some point, billions of years in the future, our Milky Way galaxy and the Andromeda galaxy will actually collide. They're moving toward each other, right? So we can say the Andromeda galaxy is blue shifting. Blue light has a higher frequency, so they're moving closer, so its frequency of this light is increasing. Right? So there's just a couple different ways to look at the Doppler effect. All right? And that's pretty much all I got for that for today. Until next time.